Hello, this is Danica,
And Jordan.
and we are here to do presentation 2 for our Engineering 460 Monte Carlo class. So the first question on this presentation is, what is Monte Carlo? The picture here to the side is the Monte Carlo building. Monte Carlo was the code name for this project or this methodology when it was being created, and it is an experiment using random numbers to find useful information. It usually involves probability distributions and algebraic manipulation. So what that means is that it's used often to find new distributions. If you're unsure what your data's distribution is, you can use a similar distribution to find the new one. It's commonly used for stock market analysis, for jet engines, especially for like jet engine failure, hypothesis testing, and nuclear physics. So what is integration? Integration is something we learned about or were introduced to in Calculus 1. It's used to find areas, volumes, displacement, mathematical modeling, and revolution volumes. The inverse of integration is differentiation. And as you go through Calc 1, everyone knows, there's more calculus after that. There's Calc 2, Calc 3. You get into these really complex maths. And this is kind of getting into the next slide a little bit, but the reason that we would use Monte Carlo is because these integrations get so complicated, they really can't be solved through integration and calculus. And then our last note here is that a definite integral is an equation that represents the integrated function, and it can be used to find the integral. So basically, if it's a definite integral, it's going to have the a and b here on our first integral, like from 0 to 3, whereas an indefinite integral doesn't have those bounds. So why would we want to use Monte Carlo? There's lots of ways that we can solve integrals analytically with calculus or with diffie-q, but some just simply cannot be solved analytically or are extraordinarily hard to do that. Monte Carlo offers an answer to these really difficult problems, and it allows us to estimate the integral so that we can find that area under the curve. It does require a distribution to sample from, though. So like I was saying previously, we usually have these distribution curves that we want to know about, but we have to choose a distribution that we already know that looks kind of similar to it. So if you use the wrong similar distribution, Monte Carlo is not going to be very accurate. Expectation using the exponential. So Monte Carlo uses the expectation of y variables for an integral to determine the area under the curve. So in calculus, when you first are introduced to integrals, you're told that when you solve the integral, it'll be the area under the curve, and then we expand that to do volumes and other more advanced stuff. But to do this for Monte Carlo, the first step is to factor out a distribution to sample from. So like I was saying earlier, you want to pick that most similar distribution. And then next, the expectation of the remaining equation is based on randomly generating random numbers from the inverse of the distribution. So hopefully the distribution is easy to inverse. One of those that's not would be like the normal distribution. We kind of have to do some funky math to get there. And then the expected value is the estimation of that integral, and we use that in Monte Carlo down the road. So why Monte Carlo is so powerful? The problem with solving analytically is that of real-world problems. So when you're in calculus class, we can use those for real-world problems. However, it can be pretty limited, whereas Monte Carlo kind of expands the amount of problems you can do. It's just powerful in that way that it expands what you can do. Some processes can be modeled using an equation, but finding the integral is super difficult. Monte Carlo allows us to get past that calculus and algebra to be able to find those really difficult integrals. And Monte Carlo offers a solution to those problems, and like on our first slide, it's often used for like stock market analysis and jet engine failure, which are pretty complex problems.
Okay, so moving on from there, we're going to go back to the Monte Carlo project. What was happening with the development process of Monte Carlo? So the first part I was using was for nuclear energy. This was fusion and fission. First of all, fusion is different from fission. Fission we haven't really discovered yet. It's kind of hard. So basically what Monte Carlo is it utilizes Markov chain Monte Carlo. So basically it utilizes something called Markov chains. A Markov chain is basically a chain of events where the drawings are dependent. The key thing there is dependent, not independent, because independent would be combinations, but since it's a dependent probability of the previous one, then it is a Markov chain Monte Carlo. So basically the example that we used for the fusion and fission is basically we are trying to find the likely travel distance of neurons through multiple materials. So basically when neurons are shot into a nuclear material, they create a chain reaction explosion if the neurons hit the center of the nucleus and basically shoot off other neurons to other nuclear material atoms. So basically what they're trying to do is they're trying to accurately predict the path of the neurons to each one of these. But this is relatively hard because they had some formulas to kind of like estimate it, but they weren't really figuring out how to exactly shoot the neuron in and what angle, everything like that, to shoot it in that it will actually produce the best results. So basically what happens with the Markov chain Monte Carlo is the neuron shooting into it is the first event, and the next neuron shooting off of that first neuron is the next event that is dependent on the previous event. So basically whenever you're having the fusion, they had to accurately predict each one of these dependent events based on the previous event. So this is where Monte Carlo came in super powerful, because it would use a probability distribution to basically estimate what way to shoot the neuron in that it would create the best results. So after explaining that, we're going to move on to our example 1.3. So we just decided to explain this in MATLAB. Basically this section is about a skips problem. Skip is basically similar to a car. That's kind of how I understood it. So basically it's almost like a car rental place. So the k variable in their example basically represents the amount of skips that they have. N is the period of time, so I just put it as a year. This x variable is the number of skips that have been rented out, or number of skips that are available. And we set the x right here as the number of skips that are available, so that's 100. Makes sense. And then we're going to have our lambda. This is the average amount of customers that are coming to get a skip. It's one skip per customer, so we have a lambda of 50. And then finally we have the probability that once a person has a skip, they keep the skip for the next day. So we put that as 60% that they're going to have it the next day. So we do for I 2 to n, we need the 2 because we have this I minus 1 right here. So we need to establish our first one. This is where the x1 comes in. And then we basically vary it until 365 days, 1 year. So first of all, we generate the y. The y is basically the how many customers are coming in that day. The r is basically the remaining amount of boats for the day, skips for the day. And then xi is the total number of ones taken out. So that would be the min of r plus y or k. So if we were to run this, we'd get these results over here with a mean of 82 skips, a sigma of 8 skips, and here is the x showing how many skips have been taken out. So with that, that's it.